So I'm going to walk through these, the quick review section of 4.4, which is dealing with derivatives of logarithmic and exponential functions. And this quick review kind of brings back some reminders of what logarithms are. I'm going to go through it pretty quickly. There's the section in the book 1.5, which is the review section on logarithms. And you can go back to your pre-calculus book and look at logarithms. And I have some other videos on logarithms as well. But maybe this will be enough to give you like a little jump start. So I'm going to start with number 1. And it says write log base 5/8 in terms of natural logarithms. So one thing we need to remember is that the common log is a log base 10. And the natural log is a log base E. But instead of writing log base E, we write it as ln. So just like when we're doing the common log, we'll write like log 3. That's assuming that that implies a base 10. You don't need to put the base 10 in there. Instead of writing ln3 we would write ln3 to represent the natural log of 3. We don't put the little base e there, and we generally don't write it as log base e of 3. So to write this in terms of natural logarithms, that is ln base e, we would use the change of base formula. So we would go ln 8 divided by ln 5. So when you're using the change of base formula, the argument of the logarithm, you take a logarithm of the top, you put that in the numerator, and the base, you take the logarithm and you put it down there. And that will give you the answer. So just to show you on the on a calculator, there is a function. Now, if I needed an actual number for this, I could push math and scroll down to h, and I have a function in my calculator called log base. So if I wanted log base 5 of 8, I want the log base of 8, comma, and the base is 5, and I put a parentheses, and I press enter, and it gives me the number answer. Well, let's try something. Let's try doing the natural logarithm of 8 and dividing it by the natural logarithm of 5. Whoops, I got too many parentheses there, I'm sorry. Let's go delete. That should do it. And I get the exact same answer. So you can see that the change of base formula works, and really it's just something you need to memorize. And generally speaking, when we're doing calculus, we're not going to want the actual decimal number until maybe the very end of the problem. So we will end up leaving things in this form a lot more frequently, or using it in that form to manipulate it. So don't be in such a hurry to get the number and go to your calculator and do the log base function. That's not going to help you solve the problems. Let's move on to quick review number 2. It says write 7 to the x as a power of e. So it's telling me I want to have e to the something here that's going to equal 7 to the x. Well, to do this, I'm going to use the inverse properties of logarithms and exponential functions, which is telling me that if I have e to the ln of x, that is equal to x. And if I have ln of e to the x, that is also equal to x. So I'll try and explain this again. I'm going to start with this one here. So if you remember, a logarithm is simply an exponent. So what this is saying, I'm going to put my exponent down here, my base right there, e, just so you can see it. So what this is asking me is saying, well, a logarithm is an exponent. What exponent do I need to put on base e in order to get the solution e to the x? Well, it's clear I need to put x on top of e to get e to the x. So that one is pretty simple. And a good way to remember how these things operate is if I have, for example, ln, and I'm going to put in the base e of e to the x. What I like to think of, and that's equal to x, what I like to think of is I can take the base right here and kind of walk it over to the other side, and it kind of pushes that x up on its shoulders, so the x becomes the exponent, and I get e to the x, and the ln just kind of falls off. So I have e to the x is equal to e to the x, which of course is true. In this version of the inverse here, well, I'm going to kind of take it apart a little bit. So I have e, but it has this exponent on it of a logarithm. Now I know that by itself a logarithm is an exponent. So ln, I'm going to put in the base e of x, is equal to something. I'm not sure what. Well, I'm going to take my e, I'm going to pull it over to the other side here. So I'm going to have x is equal to e to the question mark. Well, I've already determined that my question mark is the exact same thing as ln x. So this is the same as my e to the question mark, which I've already determined is equal to x. Now, those are a little bit circular. I understand that. So the main thing I kind of want you to remember are these two formulas, is that exponential functions and logarithmic functions are inverse of one another. And if you remember, if I have f to the f minus 1 of x, that is equal to x, or if I have f to the minus 1 of f of x, that is also equal to x. If I take one step forward and one step back, I'm going to wind up in the same spot where I began. So let's use that to solve this problem number 2. Again, I'm back here, I want to write 7 to the x as a power of e. So I could say e to the ln 7 to the x. I'm just using this one right here, and instead of just having a regular x, I have 7x. So e to the ln 7 to the x is equal to 7 to the x. But there's another property I can use to simplify it even more. You might remember this. If I have a log, one of the properties of logarithms is called the power property. So if I have ln to the of a to the 7th, for example, I'm allowed to move this power to the front of the logarithm. So ln of a to the 7th is the same thing as 7 ln a. Well, in this case here, I'm looking at my exponent here. I have a power of x, so I can rewrite this as e to the x ln 7. And that is the answer for number 2. Let's take a look at number 3. I want to know the natural logarithm of e to the tan x. So just so you can kind of see this a little bit better, I'm going to write this as ln. I'm going to put in my base e, and then I'm going to go e tan x. So logarithm is asking me a question. It's saying, well, what exponent do I need to put on base e to get e to the tan x? Well, the answer is tan x. So that is the answer to number 3. Number 4 deals with another property of logarithms. You might remember that if I have log of A divided by B. It is the same thing as log A minus log B. Well, here I have a logarithm minus another logarithm. They're the same base, so I can utilize this property. So I'm going to combine these logarithms, I'm going to condense it, and I'm going to get, well, I have one logarithm, and on my A is x squared minus 4, and my B is x plus 2. So I now have one logarithm, but I can simplify this a little bit. I can make this ln, and I'm going to make my numerator x plus 2 x minus 2, because I can see I have the difference of two perfect squares, divided by x plus 2. Well, these two, let's make my end parentheses here. These two x plus 2's are going to cancel out, and so my answer to this problem is just going to be ln x minus 2. Let's take a look at number 5. So I have log base 2 of 8 to the x minus 5. Well, looking at that, I have to realize that 8 is a power of 2. So this is really the same thing as the log base 2 of 2 to the third to the x minus 5. All right, that's going to make it a little bit easier. So let's rewrite that as log base 2 of 2. Well, since I have exponents that I'm multiplying times one another, but I'm taking a power of a power, I multiply the exponents times one another. So this becomes 2 to the 3x minus 15. The logarithm is an exponent. Logarithm is asking me a question. What exponent do I need to put on base 2 to get 2 to the 3x minus 15? Well, I need to put 3x minus 15 on 2 to get 2 to the 3x minus 15. So the answer here is 3x minus 15. Let's take a look at number 6. Well, now number 6, don't get confused. This is not log A divided by B is equal to log A minus log B, because it is not in this form. This problem is log base 4 x to the 15 divided by log base 4 x to the 12. So you see up here, it's one logarithm, and the argument of the logarithm is a quotient. Here, I have a quotient of two logarithms. Well, I think I'm going to use the power property with this one here. I'm taking a logarithm of an argument with an exponent. So I'm going to change it into 15 log 4x divided by 12 log base 4x. Well, log base 4x is the same as log base 4x, so that's going to be 1. So my answer is going to be 15 over 12, which I can simplify into 5 over 4. This problem number 7 is going to utilize a lot of the different properties of logarithms. So in addition to the quotient property of logarithms, there's the product property of logarithms, which is log A times B is equal to log A plus log B. Right? So I'm going to use a lot of the properties. I'm going to rewrite this as one logarithm. I'm going to condense it. So the ones that are positive are going to go in the numerator, and the ones that are negative are going to go in the denominator because of the quotient property. A divided by B is equal to log A minus log B. So those that are negative go in the denominator, and those that are positive go into the numerator. All right, but first I'm going to change this first one. I'm going to make it, instead of 3 log x, I'm going to make it ln x cubed. Because I need to have, in order to condense, I have to have all of them being just plain old logarithms, no coefficients. So that is going to be minus ln 3x, and that's going to be plus ln 12x squared. So now I have a situation where I have logarithms, all of the same base. They're all base E, natural logarithms. I'm going to make it into one logarithm. So it's going to be ln, and in the numerator, I'm going to have x cubed times, so this is positive here, 12x squared. And in my denominator, I'm going to have just 3x. And it's times because, again, I'm going up to the product property here. Combining a logarithm a times b is equal to 2 separate logarithms, log a plus log b. Well, in this case here, I have log a plus log b. They're separate. I'm combining them. It's a multiplication operation. So now I have ln 12x to the 5th divided by 3x, and that equals ln 4x to the 4th. And that's my answer to number 7. All right, let's do some work on these equations here, where I have to give an exact answer, and I also have to give a decimal approximation. So number 8, I have 3 to the x equals 19. Now the problem here is that my x is trapped up here as an exponent, and I need to get it down if I'm going to solve for it. So what I'm going to do is I'm going to take a logarithm of both sides. I'm going to go ln 3 to the x is equal to ln 19. Totally legitimate, just doing the same operation on both sides of the equation. But now, because of the power rule, I can change this to x ln 3 is equal to ln 19. And ln 3 and ln 19, they're just numbers. So I'm going to divide both sides by ln 3. And I get x is equal to ln 19 divided by ln 3, which is approximately equal to 2.68. So here is the answer in exact form, and here is the answer with a decimal approximation. So let's try the next one. Again, I have x trapped up here as an exponent. And the way to get it down is to do the inverse operation and take a logarithm of both sides. So I take a logarithm of both sides. So I'm going to take ln there. And so here you see I have a product. A logarithm now is a product. So what I have now is I have ln 5 to the x plus ln of ln 5. So I have a logarithm of a logarithm. Nothing wrong with that. And that is equal to ln 2 to the x. Now I'm going to be able to get my x's down. So I'm going to have x ln 5 plus ln 5 is equal to x ln 2. So just like we do with any kind of an algebra problem, I'm going to get all my x's on one side. So I'm going to have x ln 5 minus x ln 2, bringing this over. And that's going to be equal to negative, I'm going to bring that to the other side, ln 5. Factor out an x. X times ln 5 minus ln 2 is equal to negative ln 5. Divide both sides by ln 5 minus ln 2. ln 5 minus ln minus ln 2. ln 5 minus ln 2. And what I'm left with is my answer. X is equal to negative ln 5 divided by ln 5 minus ln 2. And if I want to get a decimal approximation, well, I'll do negative ln 5. I think I'll just enter that and get an answer. And I'm going to divide it by my denominator of ln 5 minus ln 2. Oh, wait, I missed a parentheses here. I always forget that the logarithm requires me to add the parentheses. So second, insert parentheses. Now I need to go to the end here and put my final parentheses there. And my answer is approximately negative 0.52. Negative 0.52. And now we'll do the last problem. I think you're probably getting the hang of it now. Since my x's are trapped up here as an exponent, I need to take a logarithm of both sides. So I just did that. Now I can rewrite this as x plus 1 using the power rule. Let's make it look like a 1, not a 4. X plus 1 ln 3 is equal to x ln 2. I'm going to distribute my ln 3, which is just a number, just the natural logarithm of 3, and I'm going to get x ln 3 plus ln 3 is equal to x ln 2. I'll get all my x's on one side of the equation. So I'm going to have x ln 3 minus x ln 2 is equal to negative ln 3. So I got my x's on that side, and I took this, which didn't have an x, and I put it on that side. I will factor out an x. X times ln 3 minus ln 2 is equal to negative ln 3. And now I have x is equal to negative ln 3 divided by ln 3 minus ln 2, which is approximately equal to. Now we'll do it together. I have negative ln 3, close my parentheses, I'll get my answer for that, and I'm going to divide it by parentheses ln 3 minus ln 2. My answer is approximately negative 2.7. This is the exact answer. This is the decimal approximation.